Hello, welcome to APL 360. My name is Jamie. This video is part of my series on the APL 360 programming language. This episode is Basics 5, Mixed Functions. It's my intention that this will be the last episode in my series of APL 360 Basics. To be sure that I cover everything for the remainder of the tutorial, this video may be a little longer than usual. I'm starting here in the terminal, and because this is a new session, I will be referencing these vectors v, m, and n, which were created in a previous session. Since these are created using random numbers, the actual numbers contained in them may be slightly different than what we've seen before. So I'll be using those a little bit later. I'm going to start by defining another random 10-element vector called Q. Q gets roll 10, row 5. So this will be, Q will be 10 elements chosen from the numbers 1 through 5 randomly. And now I want to see how many 1s are there, how many 2s are there, how many 3s, 4s, and 5s. So I'll start by doing a cross product. We'll do Q jot dot. Jot, again, as a reminder, is the little circle found by doing Shift J. Dot is the period, but jot dot together is the outer product. Then we'll do the using the equal as the comparison operator, comparing this with iota 5, which will be the numbers 1 through 5. So this doesn't give us immediately what we're looking for the number of 1s, 2s, 3s, and so on, but you might see that there's a pattern here that we can use. This cross product has the numbers 1 through 5 across the top, and the elements of Q down along the left-hand side. And then using the equal operator, wherever the elements of Q are equal to we'll call it the index value, then we'll see a 1. So Q contains 1, 1, 0, 2s, 3, 3s, 3 4s, and 3 5s. So all we need to get the number of 1s, 2s, 3s, and so on is just to do a plus reduction of this cross product. So we'll do a plus reduce of Q jot dot equal iota 5. That didn't give us the answer we're looking for. So to get the correct plus reduction, this added up the values for each of the rows in essence instead of the columns. So we'll need to use the square brackets to get the column selection. So we'll do plus reduce and then choose the first axis instead of with the default is to choose the last axis of the same thing. So Q jot dot equals iota 5. Okay, that looks better. So now it is adding these up column-wise. We get 1, 1, 0, 2s, 3, 3s, 3 4s, and 3 5s as the result. Okay, moving on to transpose now. We have our two-dimensional matrix M. We want to transpose the columns and the rows. So we'll do 2, 1, which says to swap the first and second dimensions. So the second dimension of the output will be the first dimension of the input in essence, and then the transpose operator is created by combining two symbols, and that is a circle, which is Shift O, and then we will backspace to do an overstrike with the backslash, which is the shift of the forward slash key, and then we'll do that to matrix M. So now where M had the first row was 5, 2, 1, that becomes the first column in the result, and the second row was 7, 7, 9 becomes the second column, and the third row becomes a third column. So we used transpose dyadically But this does the same thing as if we were to use transpose monadically on the two-dimensional matrix. So we'll do just circle combined with backslash to get transpose again, and then we'll do that to M, and we'll see we get the same result. So the two-dimensional, or I'm sorry, the dyadic version of transpose isn't so useful with two-dimensional matrix. There is one more use of it for two-dimensional matrices that I want to mention, which is getting a diagonal. So if we say keep the display the results, or I'm not sure the correct wording here, but produce the values where the column and the row are the same. So we'll do a 1, 1 to the left of the transpose on M. Okay, I did the wrong character there. This I did bar instead of backslash. We'll see later that this is the reverse. Well, in one case it's reverse, and monadically it's reverse, dyadically it's rotate. So I'm going to just press enter there. Okay, we'll try this again. 1, 1 rotate of M. I'm sorry, 1, 1 transpose of M will give us the diagonal, which is if we look up here at M was 5, 7, and 8. And so we get that as a 3-element vector there. Where the dyadic version of transpose becomes more useful is when we have matrices that are larger than 2 dimensions or have a rank larger than 2. So here we'll make I'm not sure what word to use, an array of rank 3, matrix of rank 3. So we'll do 2, 3, 4. T gets 2, 3, 4. Choose from iota 24. Not choose from. We're not doing random, but we'll do a 2, 3, 4 reshape of the numbers being generated here from 1 through 24. So we'll see here that T is in 3 dimensions. And so how we read this is the first matrix is in 2 dimensions, but then there's a second matrix which represents the third dimension. Now if we do a 3, 1, 2 transpose, and for me, I find it difficult to think in terms of these order of dimensions, but we can see in essence what this is doing by looking at the results. The first row of the first matrix of T becomes the first column of the result. The second row of the first matrix becomes the first column of the second matrix result, and the third row of the original matrix, first matrix, becomes the first column of the third matrix in the results. So you can get all kinds of different combinations of transposes when you start looking in higher dimensions. We can also do a diagonal section just like we did with the two-dimensional matrix M earlier. We can do a diagonal section using, again, this having two of these being the same, the 1 and the 1, transpose of T, and then we get a section out of that. Okay, we're going to set X to be an array that is, in essence, the number of degrees around a circle in 30-degree increments. And so we're going to use the circle operator to represent pi here. And that'll be followed by left parenthesis 0, comma, iota 5, right parenthesis divided by 6. Okay, So we see the numbers here, which represents in radians 0 degrees, 30 degrees, 60 degrees, and so on. So we're going to use this to get a table output of the sines, cosines, and tangents in intervals of 30 degrees. But the default number of digits that get displayed when we look at these number of decimal places is 10, and that's a little bit too many to make the resulting table that we want look nice. So we're going to set the digits using a system function here, right parenthesis digits 4. To get the results to come out in the 3 columns that we want with sines, cosines, and tangents, we're going to do a transpose of the results. So we'll do the two-dimensional, just using the monadic transpose here, of 1, 2, 3. So this, for circle functions on the left of the circle function, 1 would be sine, 2 would be cosine, 3 would be tangent, and then we're going to do an outer product. So we'll do dot dot with a circle of, so the circle being the function we're using between the 2 axes of x. So we'll see 1 representing the sine, and then the outer product doing this over each one of these numbers. Then the 2 representing the cosine over each one of those, and the 3 representing tangent over the or all those numbers in x. But instead of getting the results in rows, we want the results coming out in columns, 1 column for sine and so on. So we do the transpose here at the beginning, and then here we see those results in those 3 columns. So that's a nice way of generating a table of sines, cosines, and tangents, and then using transpose to get the output like we want. Okay, we're going to move on to rotate now. So here's Q again. We're going to rotate Q 3 places to the left. So we'll do a 3. The rotate operator is found by composing O with bar, which is shift of M. So we'll do 3 rotate of Q. And so this does a left rotate. And so where 355 was the beginning of Q and the results here, 355 is the end of the result. If you want a right rotation, make the left parameter or left argument negative. So we'll do a negation of 3, and then we'll do the rotate of Q. And so then now we get the rotate the other way, where Q started with 355. If we look at the result here, it's been rotated inward to the right 3 places. We can rotate columns and rows of two-dimensional matrices by different amounts. So I'll use the amounts on the left, 0, 1, and 2, and then do rotate of the first axis of M. So this is rotating the columns by different amounts. Let's look at what M was originally. So M started out with the first column being 574, and we're saying rotate that column, the numbers in the column 0, so that column remains the same. The second column, we're rotating 1. I guess since it's positive, that would be down. If it were negative, it would be rotating it up. So 752 becomes 275. And then column 3, rotating by 2, 819, the 8 then moves all the way down to the bottom, and so we end up with 198 for the third column. We can do a rotation of rows all by 2 to the right. So we'll do a -2, and we'll do rotate on the rows. So we'll do the second axis here of M. Now I'm not sure that the 2 is necessary. We'll look at that. Since that's the last axis, and pretty much all of the APL operators will operate by default on the last axis, I don't know that this that the 2 in square brackets is absolutely necessary, but we'll try it and see. To rotate M. Okay, so it wasn't. We end up getting the same result. But again, you might, just to be explicit, you might go ahead and put the 2 in brackets just to remind yourself or whoever else reads your code that you do specifically mean the last axis there. If we do a 1, 2, 3 rotate of M without using the bracket operator, then this is going to do a rotation of the rows. So again, reminding us of what M was. The first row was 5, 2, 1. So we're rotating the first row by 1. Yeah, is that right? Yes, rotating it to the left. So those are positive numbers, so rotating to the left. The 5 then gets rotated around the left to the end, and then we have the 2 and the 1. The second row will be rotated to the left by 2, and the third row rotated to the left by 3. If we use the rotation operator or circle bar, if we use circle bar monadically, it's no longer rotate, but is reverse. So we'll do a circle bar of, let me try that again. Let's look at Q before I do that. So there's Q again. We'll do a circle backspace combined with bar of Q. And Q originally read 35531. Now, if we read it in reverse, we see that it ends with 35531 and so on. So that's the reverse operator. You can choose which coordinate that you want to reverse along when you use reverse over two-dimensional matrix. So if we want to, this again, if we want to reverse along the first axis, reverse the this would reverse along the columns, if I'm thinking about this right. So here's M. Nope, it's reversing the order of the rows are being reversed, but within each column you're getting the reversal being done. So the first column was 475, and then that's reversed now to be 574, and so on. Or I guess vice versa. Here's M is the second matrix, and then the reversal was above. If we leave out the square bracket operator and just say reverse M, then this will reverse along each row. So in essence, it's taking the whole column doing the swap for the reverse here. So the first row is 521 in the original matrix, and the result it's 125, and so on. Okay, we're going to move now to compression and expansion. So I'm going to set U to be a logical vector, which will have the results where Q is greater than 4. Okay, that's greater than or equal to, let me try that again. U gets Q greater than 4. All right, so let's again remind ourselves of Q is up here. It was 3, 5, 5, 3, 1. So we have 0, 1, 1, 0. So the zeros represent where this is false. The ones represent where it's true. We can use the forward slash, which is called compression. And what the forward slash compression does is, using this logical vector as the left argument, it will pull out the values in Q, or whatever you're applying it to on the right, where the logical vector has ones. So we'll do U compress Q, and it pulls out the numbers that were greater than 4. And there are only 3 of them, and they were all 5s. We can do the opposite and use not U to compress Q. So not is using the tilde operator, which is shift T. So we'll do not U, and then we'll put that in parentheses, and then do compress Q. So then this pulls out everything that was 4 or below. If we want to sum the how many elements of Q are greater than 4, we could do, so this is not, sum isn't the right word, this is a count of the number of elements of Q that were greater than 4. We can just do a sum reduction of U. Now if we want to get the sum of those numbers, the sum of the numbers in Q that are greater than 4, we do a plus reduction of U compress Q. So those were the 3 5s, so this total here is 15. We can use compression along different coordinates of M for our two-dimensional matrix. We'll do 1, 0, 1, compress along the first axis of M, and this pulls out the first row and the third row of M. But we have a 0 there for the second row, so we don't see that in the results. If we do it along the last axis, we'll do 1, 0, 1, compress M without the axis designator there. Then it's pulling out the column. So we get the first column and the last column of M. If we want to look at what elements of M are greater than 5, we need to do what's called a Ravel. So on the left here, we'll do a comma, which takes the two-dimensional matrix M and puts the elements in order next to each other in row major order, and making it a vector instead of a matrix. So M greater than 5. So that'll produce our logical vector on the left, and then we'll compress that with the Ravel again of M itself. And so this pulls out the values of M that were greater than 5. And so there are 4 of those, 7, 7, 9, and 8. We can do the opposite of compression, which is called expansion. So I'm going to make an expansion vector here, V. V gets the binary digits 1, 0, 1, 0, 1. And then we will use V backslash iota 3. So this is expansion, and we'll see what it does. So iota 3, again, as a reminder, is the numbers 1, 2, 3. And so where there is a 1 in the expansion vector, we will get an element of the vector on the right. So we get a 1 for the 1, then 0 just becomes a 0 in the output, and then where we had a 1 in the third position of V, we get the next element of iota 3, which is a 2, and then a 0, and then we get the 3. We can do an expansion over our matrix M, so we'll do V backslash M, and this will give us the columns of M separated by the two columns of zeros. If we do a character vector, so we'll just look at what the ABC displays as. So they're just the letters ABC, but we'll do an expansion with V expand the character vector ABC. Character error. Let's check that again. V expand ABC. Okay, I'm not sure what happened earlier. Maybe I put a space in there between the two, or something happened by accident. So with the character vector on the right for expansion, the zeros become spaces. And so I just wanted to show you above, there was ABC without the spaces, so that you can see there is, extra space between the A and the B, and the B and the C. Okay, now we're going to move on to the operations decode and encode. We will use the upward tack and downward tack symbols for these. So we will do a base 10 decode. So we'll do 10, and then this is shift B for that upward tack character, and then do 1 space 7 space 7 space 6. So this does a base 10 decoding of 1776. So in essence, it's doing what you would do if you were taking these 4 digits separately, and what operation would you need to do to get them back into the number 1776. So we're taking the 6 and multiplying it by 10 to the 0 power, the first 7 by 10 to the first, second 7 by 10 to the second, and then the 1 multiplied by 10 to the third, and then adding all of those together. And so we do get the number 1776 coming out of that. We can do other bases. I don't know. Again, so some of these aren't, to me, that the immediate use doesn't become that self-evident. But if we do 8 decode 1 space 7 space 7 space 6, and then in base 8, that number is 1022. We can do, instead of the upward tack, we can do a downward tack, which is encode. So we're going to do a 4-digit base 10 representation of 1776. So this is reverse of what we just did. So on the left-hand side, to get the 4 tens quickly, we can do 4 reshape 10. That will give us 10, 10, 10, 10 in essence. And then we will do shift N to get the downward tack of 1776. And then coming out of that, we get the 4 digits that made up that number in base 10. So we use a 10 for all 4 of the digit places to get that. Now we'll see that this is useful later if you want numbers that aren't necessarily the same base in each of those places. If you don't put all 4 tens on the left, so here we'll just do a 3 row 10 in parentheses, and then do the encode of 1776, then it leaves out the 1 on the left of that. You don't have to use the row operator on the left. We could do 2 tens, which would be in essence 2 row 10 of encode 1776, and as you might expect, we just see 2 digits coming out of that, the 7 and the 6, 1, 10, only produces the 6 in the ones place there. Now we'll do a mixed base values of 24, 60, and 60. So we'll do these on the left, 24, 60, 60. So in essence, this represents 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. To C, then we'll do a decode, Shift B, of 1 hour, 3 minutes, and 25 seconds. So we end up with the total number of seconds in that amount of time, so 3,805 seconds. We can reverse that process with encode. So we'll use the same set of bases on the left, 24, 60, 60, but we'll do a Shift N for encode and then provide the same number we just ended up with, 3805, and we'll see this is the inverse operation. And we get back that that's equivalent to 1 hour, 3 minutes, 25 seconds. So I quite like that. Of course, this works great with binary numbers. We can do base 2 and do a decode of 10110, and that's equivalent to 22 in decimal. Okay, I'm going to define a vector P and then do some permutations. So I don't have P defined. So let me define P is 2, 3, no, let me try that again. P gets 2, 3, 5, 7, 11, 13. So I'm remembering now P was prime numbers. So we've got 6 prime numbers there. So we can use iota in a dyadic form as index of. So we'll do P iota 7, which in essence will tell us in P what index is, at what index is there a 7. And that tells us that at index 4 there's a 7. Let's see what we get for a number that's not in P. We'll do P index of 6. So where is 6 in P? So we end up with 7. Now P only has 6 digits, so the 7 is APL 360's way of telling us that it didn't exist. So it gives us a number that's 1 larger than the length of P to tell us that. We'll do show us, give us the indexes of 4, 5, 6, and 7 in P. And so we see that P does not contain a 4 or a 6. Those are not prime numbers. But 5 was element 3 of P, and 7 was element number 4. Okay, we're going to create a permutation vector Q. So a permutation vector is a set of position numbers. So first position, second, third, fourth, and fifth, and so on, arranged in some order, but being sure to include all of the positions. So this will be positions 1 through 5, but in this particular order: 5, 1, 3, 2, 4. we can get um, we can create a permutation inverse to Q with this following piece of code. R gets Q iota iota row of Q. We'll look at R. I see I made a mistake with my original Q, so let me go back and redefine Q. I left off I put a 5 at the end instead of a 4. So Q gets 5, 1, 3, 2, 4. Okay, now we'll try R again. R gets Q iota iota Q. Okay, so now we will we'll take Q and apply R. Oops, Q in square brackets. So give us the elements of Q in the order of R, and we'll see why it came out to be the inverse. So this gives us the in essence, the original positions, 1, 2, 3, 4, 5. Okay, we're going to use a character vector now with the letters A through Q. A gets quote A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. We can use comma to combine A with the rest of the alphabet. So A gets A, comma, and then in quotes R, S, T, U, V, W, X, Y, Z. We'll see A contains the complete alphabet. We'll use index of to say where's C located at. A, iota, character C. It's the third character. We'll do J gets A, iota, CAT. So where are the letters for cat in A? We'll use that J as a vector to index into A. I didn't want to do that. I just lost my alphabet. A gets A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Okay, A indexed by J. And then we get back the letters of cat coming out of that. We'll do a matrix of characters here. M gets a 3 by 5 matrix reshape of the phrase 3 short words. And we'll look at M. M then now has 3 rows of 5 characters each. We'll get the ranking of M using our alphabet A, so they'll assign that to J. J gets A index of M. We'll look at J. We'll index the alphabet again with this selection vector J. I don't want to do that. A left square bracket J. And we get back 3 short words coming out of that. Okay, just some other mixed functions, and then we will be finished in just a couple minutes here. Using the question mark operator for roll, like rolling, meaning like roll dice or getting random numbers, we can say give us a random choice of 3 out of 5 without replacement. So that'll be 3 roll 5. If we try to use a number on the left that's larger than what we're giving on the right, we'll end up with a domain error. If we use the same number, we should get the same digits in a random order. So we'll do 5, roll 5. So then, in essence, this gives us a random permutation vector, or the numbers 1 through 5, but in a random order. If we do that again, they should come out in a different order. Again, this works because we're using it dyadically here, meaning choose without replacement. So we're going to do this for the numbers 1 through 8. We'll say x gets 8, roll 8. Okay, there's that. We will do a grading, which is a way of producing a sort. So we're going to do a grade up, which is a delta symbol. So we're going to do Shift G. Nope, that's del. We'll do Shift H to get delta. Backspace combined with the vertical bar, Shift M. So this is called grade up. Grade up X. So this gives us a grading vector, and I don't really know where that term grade comes from, but it is kind of an ordering. So what is it telling us? So if we look at the original vector x, we see in the third position there's the number 1, and in the 7th position is the number 2. In the 2nd position is the number 3. So if we look at the resulting of grading x using grade up, we see the order 3, 7, 2, because if we were to put these in order, x in order from smallest to largest, we would need to take the 3rd item, then the 7th item, the 2nd item, the 4th item, and so on. So if we use the grade of x as an index into x itself, so we'll do x grade, and then in square brackets, try that again, x square brackets with grade up of x. Then this will do a sorting. So APL doesn't have a specific character symbol that represents sort, because grading is actually more powerful. We can use the grading vector to sort other vectors in the same order that we would get using x here. If I think of an example here, if you have one vector of first names and another vector that represents maybe the wages. First names isn't good here. Maybe full names in one vector, and you want to sort those in order by alphabetical order, but they're connected to the ordering of wages in another vector, and you want the wages to be sorted in the same order that the names would be sorted if they were sorted in alphabetical order. So you could use the grade of the first vector on the second vector to get the numbers in the same order as the names if everything was put in alphabetical order. I hope that makes sense here. We can do grade down to do something in descending order. So we can say grade x. No, I'm sorry, take x with the indices of grade down. So we'll do delta backspace. Oh, that's the wrong one. Okay, we'll try this again. X left bracket. Now we'll do del, which is Shift G, because we want grade down. So we'll do backspace Shift M of X. And now we get them in descending order. Okay. Another operator we're going to look at before we end, and this will be the last one, is membership. So we'll say U gets A, remember A is the alphabet, and then we'll do epsilon, Shift E, which is member of, and then now is the time. Okay, so out of the whole alphabet, um, in the phrase "now is the time," what letters are represented there? So if we just look at U, we get a vector that's 26 long with zeros where none of those characters were represented in the phrase and ones where they were. So if we want to see where those are, we can do a compression. We'll do a U/A, and we see what those letters are then. Now is the time contains E, H, I, M, N, O, S, T, and W. We can use this member on number vectors as well instead of character vectors. So we'll do iota 8 on the left and look at where in that vector do we have the numbers 3, 7, and 5 represented. So we see this here. It doesn't matter, if you have multiple numbers on the right, it shouldn't affect multiple copies of the same number on the right shouldn't affect the results. We'll do 3, 7, 5, 3, 7, 7, 5. So we have 7 twice, and it's only going to show up once in the result because this is just pointing out what individual numbers do they show up at least once in the number on the right, and then you can see that resulting vector there. Okay, that's it for finishing the tutorial at the end of Appendix A of the APL 360 manual. My intention is to produce some more advanced videos, and I hope that you will stay tuned and watch those when they come out. Thank you for watching this video.